Hello, everybody. Thank you for being here. Today, I'm going to present to you AI Epilepsy, a project we are currently developing in La Universidad de los Andes in Bogotá, Colombia, in collaboration with Fundación Hospital Pediátrico La Misericordia, also known as OMI, which is a children's hospital back in Bogotá, and private company Biotecnología y Genética SAS, all with funding from the Colombian Ministry of Science. So, as a brief introduction, epilepsy is a neurological disorder characterized by an excessive and synchronic signaling between neurons and an increase in brain electric activity. This leads to what we know as seizures, which causes symptoms like loss of awareness and disturbance in movement. It is a non-communicable disease. It can affect people of any age, and it's estimated that 50 million people worldwide suffer from this condition. As of today, there's a lot of different information sources for epilepsy diagnosis, such as medical records from patients, neuropsychological tests, also electroencephalograms or EEGs, which measures brain electrical activity in different regions, MRIs, that are images when we can see brain structure integrity, and finally, peripheral blood microRNA sequencing, where we look at potential biomarkers for this condition. As of treatment, the first course of action is to prescribe anti-epileptic drugs. These are long-term therapies. Unfortunately, 30% of patients doesn't have like a positive response to these therapies, and they have to go through two different regimes of these drugs before they got diagnosed, like refractory epilepsy patients. After this, there's a necessity to find the epileptogenic node and a later extraction through surgery. So with our developing group, we conducted several interviews and processes of observation in OMI, and we found a lot of improvement opportunities. To name a few, EEG and MRI data analysis are complex and require a large amount of time and medical training. There are no diagnostic tools to integrate all types of data, and early diagnosis of refractoriness improves quality of life and prognosis for patients. So our proposed solution is AI Epilepsy, a user-friendly web application that integrates ML, machine learning, and deep learning models, and it's meant to use in a clinical context. So what are some of these functionalities that our software already has? First of all, for data management, we have functionalities like patient search and also a layout to see patient information summary and medical records. Also, we can associate diagnostic files with patients and perform analysis on patient data asynchronously. Sorry. So we achieved this. We achieved it by implementing this software architecture consisting of 5 different components. So first, we have a monolithic application where we have the front end and the back end. Then it is connected to hospital servers where we get patients' information, and also to 2 data servers, one for structured data, where we store analysis results and new patient information, and storage where we have patients' files. Additionally, it is connected to what we call an ML component, machine learning component, through a messaging queue. In this component, we run all the data analysis. So we also integrated an MRI viewer from people of EPAN. It's a really interesting tool, which includes functionalities like area, distance, and angle measuring, and also does 3D reconstruction. Another functionality is an EEG seizure classification. To do this, we take these 3 public databases consisting joining them, we have more than 500 hours of EEG and with annotations for seizures. So we take all this data and we needed to prepare it for a machine learning design experiment. So we first took it and changed the configuration for all of them to be in a bipolar configuration. After that, we did subsampling, so all files are into 56 hertz. Then we did a filtering with a high pass of zero point 0.5 hertz and a low pass of 70 hertz and a notch of 50 or 70, depending on which country the database is. And after that, we did C normalization. And finally, we divided all the files in 5 seconds fragments and divided it into different classes, seizures and no seizures, according to the annotation available. At the end, we had 9,522 elements in each class. With this data, then we went to train our models. So we took 90% of the data. So first we have approaches in machine learning models in which we calculated 8 different feature subsets, and a ninth feature would be the combination of all the 8. And then we trained 5 different models with classic machine learning algorithms like random forest, support vector machine, KN neighbors, sorry, decision tree classifiers, and naive Bayes. And on the other side, we did 5 different neural networks architectures. That are there like 2 convolutional neural networks, one fully connected convolutional neural network, a deep convolutional neural network, and lastly, autoencoder and a recurrent neural network. At the end, we test all these models with the 10% of the data. And our metrics for choice was F-score and OutRock. So these were the results for this model. So our best 2 models were one convolutional neural network, from which we got an F-score of 0.923 and an OutRock of 0.978. And the other one was a random forest with the feature of the combination of all the subsets. This got a F-score of 0.918 and an OutRock of 0.975. So at this point, we believe we already have like the problem solved because we got good metrics and a good performance. So we decided to test with some hospital-owned data, and these were the results. So basically, this data, the data consisted of 5 hours of duration, and we tested the best 6 models from the past step. And we saw that there was like a really, really big decrease in performance, having an F-score of 0.7 and an OutRock of 0.765, sorry. We believe this is because there is a lot of artifacts related to movement of the patients, but we are waiting for some more data to prove this hypothesis. Another functionality is MRI lesion location. In this case, we have 3 different models depending on the anatomic plane of the images. So basically, there is MRIs that we calculate an descriptor called histograms of oriented gradient. After this, we do a dimensionality reduction with PCA, and finally, we do classification with a support vector machine. And the final classes were the hemisphere where the lesion is, and if there is no lesion. These are like the results for this, like the performance of these models. So for the sagittal anatomic plane, we have 94.7, for the coronal 81.5, and for the transverse 84.7. And finally, for microRNA sequencing, we initially conduct the analysis by implementing the NF-core small RNA-seq pipeline. The data we took from there was the Mirna expression profile calculated over that gives MIRDIP2. And with that, we can put it in our software, and with an already made potential microRNA biomarkers list, we then showed if there's presence for these biomarkers in the patient. So what are we working on right now? It's in integrating an EEG viewer and state-of-the-art brain anomalies detection models in MRIs. We want to also integrate some models that has all kinds of data to predict refractory epilepsy. And also we want to have like this final version to do software validation with potential final users. Thank you.